everyone, and welcome to another topic webinar. Today's topic is going to be on the desolvation of samples as a route to new crystal forms in organic, inorganic, and hybrid materials. We have three speakers sharing the presenter role today. We have Katarzyna Ślepokura, Oskar Kaszypowski, and Vasyl Kincheballo, sorry, I apologize for the poor pronunciation. They are from Wrocław, so two from University of Wrocław and one from the Institute of Low Temperature and Structural Research. Just before we start, if you'd like to ask questions throughout the presentation, please do. We'll collect them together at the end and I will ask them to the presenters directly. Please use the Q&A button to ask questions. I might miss them if you put them in the chat. I'll try to keep an eye on both, but Q&A is where you should ask questions. I just also want to invite you to join our forum if you haven't already. If you're a Rigaku customer, you're entitled to join our forum, and that's a place where we have lots of useful information. You can download our software and access old recordings, things like this webinar, and from our Rigaku schools and so on. So that's all I wanted to say today. I will stop sharing and pass over to our presenters today. So if you can hear me and you're ready, please share your screen and start whenever you're ready.
Thank you, Fraser. Hello, good afternoon, everyone. We are very happy and honored to be here today and to present some of our results, our findings on crystal dehydration. Perhaps you are familiar with the cave of the crystals in Naica, Mexico, where hydration-related transformations are evident. Beautiful selenite crystals, which are huge, up to 12 meters long, grew there for at least 500,000 years when about more than 20 years ago, miners drained the cave and exposed the crystals to air, the dehydration of these large selenite crystals started, and basonite, which is calcium sulfate hemihydrates, started to form. So dehydration in this cave of the crystals causes dulling, microcracking, and the weakening of the mechanical structure of these giant gypsum formations. I should also say that in general, the loss of water of crystallization from hydrates is a common and quite often spontaneous phenomenon. The main factors causes dehydration is, of course, temperature, elevated temperature, and reduced humidity, but in general, dehydration can also be triggered by other factors like pressure or even radiation. In some cases, of course, the effect of dehydration may even depend on how fast you heat the crystal. Water molecules can either be tightly bound in the crystal by the main components of the crystal, like organic molecules or ions, or they can be located in channels or layers like here. That is why the structural outcome of dehydration varies significantly among crystals. Fortunately, in some cases, dehydration proceeds with the retention of structural integrity. I mean, according to the single crystal to single crystal mechanism, which is good because structural investigations can be easily performed using single crystal diffraction. But unfortunately, in other cases, we observe crystal cracking or powdering with the formation of polycrystalline samplers with larger or smaller grains or crystallines. And in such cases, structural studies become significantly more challenging, and we need to employ other techniques like powder diffraction or electron diffraction. In these cases, we receive great support from Jakub Wojciechowski, with whom we have been cooperating for several years. In many cases, our crystals are small and sensitive even before dehydration. In addition, we often crystallize using hanging drop methods. So that is why we have a very limited amount of material. Some of the samples also contain powdered material, which we want to characterize as well. Therefore, we often conduct powder analysis on microsamples. We measure our crystals mainly on a single crystal diffractometer with intense copper radiation from rotating anodes. We use it to investigate both single crystals and powders. Sometimes, when crystals are too small for synergy DW, we utilize electron diffraction and synergy ED. Why are we interested in dehydration? First, we are looking for new ways to obtain new crystal forms, just to understand and control structure and polymorphic diversity in materials. Second, we aim to prepare and investigate the structure of anhydrous or at least partially dehydrated forms of systems that are usually hydrated, like nucleotides. Why? For instance, to modify the properties such as water solubility. And today, Vasil will present you some examples of hypodiphosphates crystallochemistry, and Oscar will share some examples of our research in the field of nucleotides. But first, I will introduce nucleotides. They consist of sugar parts of purine or pyrimidine base and phosphate groups, one or more, and they may be located in different places. Nucleotides play a fundamental role in the function of all living systems, but first of all, of course, they are building blocks of nucleic acids, DNA and RNA. But they also regulate metabolic pathways, energy transfer, signal transduction, and so on. They are also essential components of many antiviral and anti-cancer drugs and food additives. As a result of our collaboration with Dr. Judith Poner from the Institute of Biophysics of the Czech Academy of Sciences, who is an expert in prebiotic chemistry, we decided to incorporate the structural description of nucleotide dehydration into the framework of research on non-enzymatic solid-state nucleotide polymerization. It is believed that supramolecular ordering, such as crystallization, promotes selection and non-enzymatic polymerization of nucleotides, and thus provides an effective pathway to the emergence of life. It is known that by just elevating temperature to about 18 degrees, you can give enough energy for nucleotide polymerization. One of the cyclic nucleotides, cGMP, which is shown here, is known for its significant polymerization potential in solid crystalline form. Thus, quite long RNA strands may be formed without the use of enzymes or other catalysts. By the way, cGMP crystallizes very easily on drying. And what is important, the polymerization of cGMP is believed to be favored by its unique crystal structure. Crystalline cGMP, like almost all nucleotides, contains a lot of water molecules. Therefore, when you heat the crystals, they dehydrate. So the question arises: what structure changes accompany the dehydration of nucleotide crystals? in which polymerization subsequently occurred, and what structural changes accompanied dehydration, how does these changes affect polymerization efficiency. To gain the deeper insights into the cGMP crystals or crystalline forms, we prepared two hydrated polymorphs. Then, by applying elevated temperature, we successfully obtained and characterized as many as 10 different crystalline forms of this nucleotide. Most of them were hydrated forms, but two of them were anhydrates. We recorded huge structural changes within the crystal of the nucleotide. These modifications were minor, but they subsequently become more pronounced as small water molecules left the crystals. The hydrogen bonding network underwent a slight rearrangement, but what is truly remarkable here is the large change in conformation. First, nucleotide base flipped, and then it rotated slightly back. Then the OPO-CCC six-membered ring adopted very rare conformation, followed by even more unexpected one. In the CSD base, no other nucleotides containing such a ring has ever been observed with this conformation. And now, with this structural information in hand, we could finally understand the all of the structural transformations observed previously by PXRD. Okay, and that's all from me. Now Oskar will present more examples of nucleotide dehydration studies. In fact, he investigated most of them by himself.
Okay, so hello everyone. It's a great pleasure and honor to be here and share with you some results from the Wrocław. Now I will begin the second part of the webinar, which will be focused on the dehydration of nucleotide crystals. These compounds have interested crystallographers from Faculty of Chemistry at the University of Wrocław for many years. While our research covers many different nucleotides containing different nucleobases, this section will mainly focus on adenyl nucleotides, which means that nucleotides contain adenine as a nucleobase, and also some examples of their synthetic analogs used in medicine. Okay, in this section, I will present several examples of crystal dehydration induced by temperature, by humidity, or vacuum. Most of these examples are naturally occurring nucleotides. At first, I will present some examples of crystals of nucleotides in acid form, and then a few examples of nucleotide salts which contain metal ions. I will present some results related to adenosine monophosphates, 5' and 3' isomers, also inosine monophosphates, as well as to cyclic nucleotides, cAMP and cGMP, as well as Tenofovir, which is used in AIDS treatment. First story is related to the acid form of 5' AMP, which was obtained as a dehydrate during the crystallization from water solution. At first, it was converted to monohydrate form, added then to the anhydrate using both temperature and atmosphere of nitrogen assigned the diffractometer. What is important, the anhydrous form, the last form, did not rehydrate in the air into initial form, but dissolved in the higher humidity. From the structural point of view, these three forms at the first glance look very similar. Nucleotides units form some kind of stacks stabilized by pi-pi stacking and hydrogen bonds between the stacks. As a result of partial and then complete dehydration, changes were observed both in the crystal architecture and hydrogen bonding. This primarily concerned the interactions between the first adenine and phosphate groups, and second between the neighboring phosphate groups, leading to a significant change not in the architecture but in the conformation of the AMP unit. In the anhydrous form, the brown one, the nucleotide adopted a very unusual conformation, particularly regarding the position of the phosphate relative to the sugar moiety. To the best of my knowledge, such a conformation has never been observed, at least in the CSD database. So the dehydration looks like a technique providing some unique examples of nucleotides geometry. Some studies were also conducted on the another adenosine monophosphate isomer, 3' AMP, for which two series of crystals were obtained, monoclinic series and orthorhombic. The first one, monoclinic dehydrate, described in the literature many years ago, was converted into two anhydrous polymorphs, alpha and beta. Importantly, each of these polymorphs was obtained under very similar conditions, but never as a mixture at the same time, always only one of them. Sometimes the dehydrate crystals, especially when they were quite big blocks, broke apart during the heating, but usually only into a few smaller fragments, which were still measurable using single crystal diffractometer, because the size of the crystallized it was big enough to treat this crystallized like a single crystal. Both anhydrous forms, alpha and beta, underwent rehydration to the initial form, but the air with the, let's say, normal humidity level wasn't enough to hydrate the crystals. The anhydrous forms had to be placed in a container and saturated with water vapor. And what is also important, we never observed the formation of monohydrate form connecting the dehydrate and one of anhydrous form. The anhydrous form alpha exhibits many structural similarities to the dehydrate, and basically the only difference is the lack of the water molecules in the crystals. But the beta form is completely different in many points of view. It differs in hydrogen bonding, crystal architecture, nucleotide conformation, and dehydration of the dehydrate to the beta anhydrous form is a quite unique and quite rare example of a single crystal to single crystal transformation accompanied by such significant structural reorganization. And as a result of dehydration, the position of the adenine relative to the ribols changed significantly, especially in the beta form, as well as the conformation of the whole sugar ring, resulting in the change of the position of the phosphate group relative to the sugar moiety. The second series of 3' AMP, the orthorhombic one, we obtained a monohydrate of this compound using also solution crystallization. The monohydrate always crystallized as a multiple twin, which posed some difficulties during the measurements. And heating the monohydrate form resulted in sample amorphization. So we believe it was quite anhydrous, but not really. If you know what I mean. So we present some composition of the crystals with 1/10 water molecule per one nucleotide unit. Interestingly, the loss of the water from the monohydrate resulted in the disappearance of twinning. This was not a result of heating the monohydrate itself, because during the heating of the anhydrous form, the twinning did not appear again. During the cooling, the hydrated form retained a quite high quality single crystal diffraction pattern, and after rehydration, this diffraction pattern deteriorated once again. From the structural point of view, dehydration did not cause significant changes in the crystals, except for the rearrangement of the disordered hydroxy metal group of the AMP, and the overall crystal structure and crystal architecture was preserved. There was also no change in the conformation of the nucleotide units after and before dehydration. One of the part of the research was focused also on the nucleotide analog, which is called Tenofovir. It is a drug used in AIDS treatment, and Tenofovir crystallized from water as a non-stoichiometric hydrate, and the most common forms observed were those with different water content. Usually we observed crystallization of few forms with different water content at the same time in the solution. All of these forms had very similar crystal architecture, and water molecules here marked with red were located between the Tenofovir layers, with another type of the water which was located inside the layer of Tenofovir. And these water molecules located between the layers, the red ones, could be easily removed from the crystals by gradual heating, yielding the alpha monohydrate without any water molecules between the Tenofovir layers. However, the alpha monohydrate form was quite unstable and underwent an irreversible phase transition to beta monohydrate above 330 kelvins. This transition was always accompanied by powdering of the sample. Beta monohydrate is the thermodynamically most stable form, and it is also available commercially. To obtain the single crystals of beta monohydrate, we had to use crystallization from strongly acidified solution. And these two polymorphs, these two monohydrates, differ significantly in both crystal architectures and intermolecular interactions, as well as Tenofovir conformation. And it is therefore clear that alpha to beta transition did not follow a single crystal to single crystals mechanism. The full cycle of transformation of different Tenofovir hydrates was also confirmed by a variable temperature micropowder diffraction measurement. And during the heating, the formation of another first unknown form was observed, here marked with green. This was suspected to be the anhydrate, and it was conferred using an electron diffractometer, in which a powder sample of beta monohydrate was placed and dehydrated using vacuum and let's say room temperature. And using few data sets, it was possible to determine the crystal structure of the anhydrous form of Tenofovir. However, the anhydrate proved to be quite unstable and highly hygroscopic in the air. So when exposed to the air, it rehydrated to the beta monohydrate in a few minutes. So it was the second proof that the beta monohydrate can be treated as the most thermodynamically stable form in this group of hydrates. Moving to the next section, in which I present nucleotides in form of salts. I will present some examples related with, for example, inosine monophosphates. And the sodium salts of this nucleotide provided an interesting example of usefulness of dehydration in structural analysis. Crystallization from water yielded a hydrated sodium salt, but with unknown composition, both in terms of sodium and water composition, mainly due to the disorder of them. And partial dehydration allowed to metal ions and water molecules to become much ordered, allowing the crystal composition to be determined. Another example is related to two cyclic nucleotides, cyclic IMP and cyclic GMP, in which dehydration resulted in crystals with quite unusual coordination environment of the metal ions. In the first case, partially dehydrated crystals of the magnesium salt of CAMP was obtained, in which magnesium ion became bound by additional phosphate group and only one water molecules, getting the coordination number from 6 to 4. In the second case, in the case of the calcium salt of cyclic IMP, anhydrous crystals obtained by single crystal to single crystal dehydration were formed and the metal ion in these crystals was surrounded only by nucleotide units, 4 oxygen atoms of phosphates and 1 nitrogen atom of the adenine fragment, resulting the coordination sphere for calcium without any water molecule. And in the last example, in the sodium salt of cGMP, the metal ions were first surrounded only by water molecules, but during dehydration, 2 adjacent nucleotides bound a sodium ion, getting the coordination number from 6 to 4. Okay, and right now I would like to thank you for your attention during this part related to the nucleotides crystals. And I would like to invite you to listen Dr. Wasyl Kinżybalo, who will present some examples of dehydration of inorganic and organic salts of hypodiphosphoric acid.
Good afternoon, everybody. My name is Wasyl Kinżybalo. I work at Institute of Low Temperature and Structure Research here in Wrocław and cooperate with University of Wrocław on dehydration of hypodiphosphoric acid salts of organic and inorganic cations. So it is quite an seldom occurring acid, quite exotic, though it has been discovered already almost 150 years ago by Theodor Salzer in Germany. It was discovered by controlled oxidation of red phosphorus in basic medium in order to give disodium dihydrogen hypodiphosphate solution. It has phosphorus in the oxidation state of +4, which is more or less stable, but unfortunately on heating up hypodiphosphates, they transform into more stable salts of phosphorus +3 and phosphorus +5. Hypodiphosphoric acid contains direct phosphorus bond. Usually it occurs in the crystal structures in the staggered form, but very, very seldom it transforms into the eclipsed conformation. So I would like to focus on hypodiphosphates of organic in this case, aminopyridinium salts, 2-amino, 3-amino, and 4-amino pyridinium salts, which were recently published in the series of 3 publications. And with the use of dehydration, we were able to systematically study the whole structural landscape of aminopyridinium salts. Some of the anhydrous salts were obtained only by dehydration, and despite numerous tries, we were unable to obtain them from the usual crystallization. So going to 2-aminopyridinium hypodiphosphate, we have the series of 7 substances. The first one, which was a dihydrate, has underwent gradual dehydration concerned with the breaking of the nice monocrystals into the multi-domain micro powder crystal. So ordinary structural description using single crystal diffraction was not so easy, but we were able to select tiny monocrystals in the size of 1/100th part of the millimeter and study them by the use of rotating anode diffractometer and determine their crystal structure. So here the structural changes from substance 1 to 3 are maybe not so big, but they result in the breakage of the monocrystal in order to produce the micropowder crystal. In case of this other substances like this one, number 4, with another composition, another ratio of 2-amino hypodiphosphate to aminopyridinium hypodiphosphate dihydrate, we were able, by the use of variable temperature powder X-ray diffraction, to follow the changes which first go as the dehydration into substance number 5, anhydrous, and afterwards at more elevated temperature, we have found that it transforms in the diffraction patterns. You see the blue diffractograms of the substance number 3, which has completely different ratio of 2-aminopyridinium versus hypodiphosphate. So it means that on heating, 2-aminopyridinium was partially removed from the sample. So by the systematic study of the system, we were able to identify all those substances by powder diffraction and know what are the transformation routes at elevated temperature. 3-aminopyridinium hypodiphosphates were dehydrated with the use of also variable temperature powder X-ray diffraction technique, but with the use of the microsample. So on the very small amount of sample, which was put to the single crystal diffractometer, and the volume of the sample of around 1 monocrystal was heated up in order to follow the dehydration routes. So here we see that the compound number 3, which is the dihydrate, has transformed into the anhydrous sample of 4, which has the very similar composition but without water. And what is the most important here is that centrosymmetric substance, which was a hydrate, substance number 3, has turned into the polar crystal of 4. So we see here that dehydration has led to the spontaneous arisal of dipole moment in the crystal structure. Going to 4-aminopyridinium hypodiphosphates, we have tried to dehydrate the compound number 1, which has lost water and transformed into the not into the monocrystal but into the mosaics polycrystalline material, and the structural changes associated with this transformation are shown in the crystal packing diagrams presented here. So as you can see, the transformation of the inorganic lattice is quite big. So the fragments which were one-dimensional chains in the dihydrate due to the water removal have transformed into two-dimensional layers. Switching to another substance from 4-aminopyridinium hypodiphosphates, compound number 3, the dehydrate, it has shown a very interesting dehydration behavior because it has provided us with 3 polymorphic modifications of anhydrous product depending on the conditions of dehydration. So slow, fast heating has given us different results, and we were able to study all of them by single crystal diffraction and also to follow them by powder diffraction. So here we can see the changes which take place on transformation of the substance number 3 into 4 and 5. So we see that in both cases the structural changes which take place are very big. Very interesting example, again, polar crystal of 6 was the third product, the third polymorphic modification of anhydrous 3 was obtained, and it has turned out to be a very strange structure, crystal structure with Z' of 36, with the volume of the cell of almost 54,000 cubic angstroms, and we were able to solve this crystal structure, and here we can see the crystal packings of this material. Now we will switch to completely inorganic materials, to sodium hypodiphosphates. Sodium salt of hypodiphosphoric acid is something we get from the synthesis procedure from the oxidation of red phosphorus in the presence of NaOH. So it was very important for us to study systematically this system and to see what other compounds we may get here, and also to study the dehydration of those samples. So the dehydration of compound number 3 of monosodium salt has given us 2 polymorphic modifications, 1 and 2, which were produced in micropowder X-ray diffraction experiment in the ratio where mainly alpha form was produced in the composition, but the detailed Rietveld analysis of the powder patterns obtained processed from the micropowder experiment has allowed us to determine also the presence of the minor component of the beta polymorphic form of monosodium hypodiphosphate. So the quality of the Rietveld field, which is shown by the residual, the difference between the fit and the experimental is maybe not perfect, but it is still very good quality, which allows us to identify the components of the resulting mixture. Now we will go to the dehydration of the tetrasodium salt, which turned out to be probably the most interesting. So in case of tetrasodium hypodiphosphate decahydrate, we were unable to crystallize the anhydrous salt. It has formed in the form of nanopowder. So we have determined we have measured the powder diffraction pattern, and in order to determine the structure, to solve the structure, we have used the electron diffraction, which was very helpful in this case and has provided us with the perfect atomic model to proceed with the Rietveld analysis of this sample and to get the very nice feed values and to analyze the crystal structure of the anhydrous material. So one of the most interesting features is the coordination environment of sodium, which is almost trigonal planar with three distant contacts to three oxygen atoms of the neighboring hypodiphosphate. And the goal of this study was to the search for the new ionic conductors of sodium, which are very important nowadays in the search for the components of the solid state batteries. So we have compared the new phase of tetrasodium hypodiphosphate anhydrous, seen here on the right, with the known high temperature modification of tetrasodium pyrophosphate, so diphosphate P2O7. As we can see, the conductivity on the right-hand side of the hypodiphosphate material is almost by one order of magnitude better than the conductivity of pyrophosphate. So by the analysis of the conductivity routes, we were able to identify the differences between those materials. On the right-hand side, we can see the energetic pathway and the routes for the hypodiphosphate, and on the left-hand side for the pyrophosphate. The barriers for the two routes, the energetic barriers, which we can see here, 0.47 and 0.85, can be seen here in the conductivity. So at the lower temperature region, the conductivity goes only through this lower barrier pathway, but at elevated temperatures, new route is also enabled with the higher barrier of conductivity. So in order to modify the tetrasodium material, we have tried the dehydration of disodium dipotassium hypodiphosphate and have got the material which was similar in the structure as it could be seen from the powder diffraction. So the red and blue diffractograms correspond to the pure sodium and sodium potassium material. So we were able to solve the structure from the powder data. It has turned out that the mixed sodium potassium material crystallizes in slightly different space group. I would like to emphasize that the structure was solved from the powder diffraction collected at the single crystal machine. It has turned out that some of the positions of sodium 3, are substituted by potassium, but due to the bigger size of potassium cation, it results in the change of the conformation of the hypodiphosphate from the intermediate staggered into eclipsed, very seldom obtained conformation. Sorry. So going to the environment, we can see that the coordination environment of sodium 1 and sodium 2 has remained more or less the same, but the coordination environment of sodium 3, which was substituted by potassium, has changed drastically. So now we go to the last example, to the Tetrabutylammonium hypodiphosphate hydrate, which has shown probably the most interesting transformation on single crystal to single crystal dehydration. The structure is built or consists of infinite chains of hypodiphosphate anions, where water is being included in the form of the donor of the two hydrogen bonds, and also as the acceptor of the one hydrogen bonds. So the release of water, which takes place as the single crystal to single crystal transformation, is associated with the change in the conformation of the part of the hypodiphosphate anions into this rarely occurring eclipsed conformation. So now the concluding remarks are the following: that dehydration is the unique tool which is usually omitted by the structural chemist, but it gives the route to the crystal forms which sometimes are impossible to obtain by some other means, and allows us to study better the structural landscape of the system. Thank you all for attention, and I would like, in the name of all us three, thank our collaborators for the perfect collaboration. First of all, the Rigaku Corporation, which we have the cooperation agreement, to our colleagues from the University of Wrocław, from University of Zanjan, from Rigaku, from Czech Republic, and to our students. Thank you very much, and we are open for the questions.
Thank you very much for that. My illusion is breaking here. So we do have some questions to ask you. I wanted to first, I'll tackle them in the order they came in. So this question, I took note, came in around slide 23, 24 when Oscar was speaking. And it's how did you validate the ratio of water in is either 3.8 or 3.5 in the samples?
Okay, great question. In fact, it's really hard to validate it using only data from crystal structure, mainly due to the disorder of the water molecules between the Tenofovir layers. These compositions presented here should be treated as an approximation because, for example, using a thermogravmetric analysis, we were able only to see the non-step-by-step, but rather continuing change of the water compositions. So yeah, these compositions, especially in the middle of the groups with second and third form of Tenofovir, should be treated as an approximation, due also to the non-stoichiometric nature of these hydrates.
Yeah, so the next question was for about slide 32. So the question was, were there some subgroup relationships observed among the compounds during the dehydration process? So this was around slide 32. I think Vasil was talking at this point.
I believe not in the second part related to the nucleotides, as I will remember, but I'm not sure it took place in the hypodiphosphoric acid salts. It's not a rule. It's not a common situation to observe this situation.
Right. And I think there's only one question really here. Is the humidity a key factor in the variable temperature PXRD and variable temperature micro SCXRD, considering the sample amount except the heating velocity? Do you understand the question?
Yes, I think so. Yes, it is a key factor, but most of the results we have presented here are from experiments inside the diffractometer with the using of the temperature controls attachment. So the samples are inside in the steam of the dry nitrogen during the experiment. So we control only temperature, not the humidity. But if you will imagine the experiment inside a chamber, for example, in which we can change the humidity, for sure it will be a key factor. What we observe many times that dehydration of the crystals using, for example, hot stage microscope in the air with the relative humidity at the level of 40 or 50%, usually take place in the higher temperatures than inside the diffractometers when we have some extra additional source of dehydration of the crystal. So yeah, it is a key factor, but we didn't check it using, not in our samples, in our experiments, because almost of the experiments are provided in the dry nitrogen steam.
Okay. So that was all of the questions that we were asked. So I'd just like to thank all three of you again for the lovely presentation. Before everyone disappears, I just want to point out that when you leave this webinar, you will be directed to a survey. We would be very grateful if you can fill out that survey. So thank you once again, and we'll see you for the next topic webinar. Thank you very much. Goodbye.
Thank you very much. Bye-bye, and greetings from Wrocław to all of you.